Our second presenter today is Dr. Adam Clayton. Adam was awarded the Royal Academy of Engineering Research Fellowship in 2022. He is currently based at the University of Leeds, where he has been an associate professor of digital chemistry since 2024. His research is focused on developing digital tools to accelerate chemical research, and today he's going to talk about self-optimizing approaches for photosynthesis. So, Adam, the stage is yours.
Brilliant. Thanks very much for your introduction. And thanks also to the AIchemy Hub for inviting me to speak at the webinar today and share some of the work we've been doing at the University of Leeds, which has been focusing on autonomous reaction optimization. So I want to jump straight in with some acknowledgements. So my group's actually based within the Institute of Process Research and Development. It's a very collaborative environment between academics, both in the schools of chemistry and chemical engineering. So the work I'm going to do, the work I'm going to talk about today is very much a team effort. So I just wanted to highlight some of the key academics I work with in this area of digital chemistry, including Professor Richard Bourne, Professor Tom Chamberlain, and Dr. Gillian Thomas as well. I also want to acknowledge all members of my research group who are pictured on the right. So these are really the faces of the people behind all of the hard work. And if you want to learn more about any of them, then please do check out their personal profile pages on the link shown on the screen. So I just wanted to start by outlining some of our general research interests within the group. So one of our main focuses is developing more sustainable syntheses of small molecules. And we like to do this by making use of multi-step flow technologies. So in contrast to your more typical batch manufacturing, multi-step flow synthesis really creates a more uninterrupted network of reactions. And this helps to reduce the need to store and transport intermediates between different sites. And as such, this really not only reduces the risk of supply chain disruptions, but also reduces the carbon footprint of a process as a whole. Now, if we look at all the manufacturing processes, approximately 85% of them include at least one catalytic step within them, which means there's a very high chance that if you're going to develop multi-step processes, you're going to be looking at combining two catalytic steps together. And so we like to focus on trying to combine different types of catalysis to exploit the synergy between them. So for example, we do a lot of work on chemoenzymatic cascades where we try to combine the high selectivity of biocatalysis with the wide applications offered by your more traditional metal catalyzed reactions. Now, these are obviously very complex systems, especially when you start combining them together. So we're also interested in applying digital tools and data-driven methods, which really allow us to accelerate the development of these systems. And in particular, and the focus of my talk today will be how we're combining automated reactors and machine learning algorithms to optimize processes. And indeed, the reaction optimization is becoming increasingly important in many aspects of society. So from minimizing environmental impact to help achieve net zero targets to reducing manufacturing costs so that new medicines can become more affordable globally. So to start with, I just wanted to share sort of my first experience with reaction optimization. So I'm a chemist by training with an interest in organic synthesis. And during my undergraduate degree, I actually had the opportunity to do a one-year placement in the lab of Professor Joe Sweeney, who was based at the University of Huddersfield at the time. And during this work, I worked with his team to develop methods for late-stage functionalization of sulfonamides. And these are a common functional group in medicines, such as painkillers. And in particular, I was looking at this Suji-Frost reaction to achieve alpha allylation of these compounds. And this is a fairly typical example of a palladium catalyzed reaction, which you can see in any kind of industry. So when you come to optimize a reaction like this, and when we came to it, first thing you have to do is define what the reaction variables are. So in this case, we found that we had 6 continuous variables. So examples of these is basically anything which has a numerical input. So this included the reaction time, the temperature, and then the 4 different stoichiometries of all the different reagents used. And then we had 4 categorical variables. So these are ones which don't necessarily have a numerical input. They don't have a natural order. And so they're more discrete options. And in this case, as with most catalytic reactions, we had the actual catalyst itself, the ligand that you add, the base, and the solvent of the reaction. So we very much approach this using a traditional sort of one variable at a time approach, so where you fix all variables except one at a certain value, change that variable to see what effect it has on the response. And this basically translated to each day in the lab, we would perform a reaction, do some sort of purification, so column chromatography, and then some form of analysis. And in retrospect, this isn't particularly efficient, and you sort of get through one reaction a day at best. This is especially the case if you take into account the fact that if you assign each of these variables 10 different levels, this would actually correspond to 10 billion possible different reaction combinations. And so what we really need to develop is quicker and less laborious ways of optimizing these kinds of reactions. Now, our group, like many at Leeds, likes to develop our approaches based on flow chemistry, which really over the last couple of decades has become quite well known, enabling technology for synthesis. So it offers general benefits such as enhanced heat and mass transfer and safer use of hazardous intermediates. And there's lots of reviews now out there about flow chemistry in general, which if you're interested, I would suggest you read those. What I'm going to focus on today is really the benefits of flow chemistry from the perspective of reaction optimization. So these for us is basically access to a wider range of reaction variables. So it's very easy to operate your flow systems under much higher pressure, and this ultimately gives you access to much higher temperatures, well beyond the boiling point of the solvents. And so you can start to optimize in this more intense process regime. You get much more precise control over your reaction conditions. So by using pumps with very accurate flow rates, you can very finely tune the residence time and stoichiometries within your reactions. And this means you can produce very reliable data from these platforms, ultimately for putting into your machine learning models. And the flow systems are also very amenable to automation. So the reaction stream, for example, can be directly sampled by a range of analytical techniques without any kind of human intervention. And this provides almost a real-time feedback of your system, which can then feed into your subsequent decision making. So this video just shows what one of the general self-optimization platforms looks like at Leeds. So we use these dual piston HPLC pumps generally to deliver each of our different reagents in different ratios. And then these will flow through a reactor. In the video, this is a temperature controlled reactor, but could be anything. So it could be electrochemistry or photochemistry, for example. And then we use some form of analytical technique, usually HPLC. And then we can use the peak areas from these chromatograms to calculate our response or our objective. And this can be fed directly into an optimization algorithm, which closes the loop by suggesting the next set of reaction conditions to run. And then the idea is this process repeats iteratively, doesn't require any human intervention, and you hopefully can come back and you have the optimum of the system found for you. Now, obviously, because these systems are being driven by the optimization algorithm, the efficiency is directly related to the performance of these algorithms. And so the next question then becomes, which algorithm should we be using in different cases? So one of the first algorithms which was sort of applied to these systems was actually developed way back in the 1960s. It's called simplex. And in this relatively simple approach, what you have is a polyhedron with n+1 vertices, where n is your number of variables, and each vertex corresponds to an experiment. So in this simple example I've put up here, we've got a two-variable system. If you have n+1 vertices, your polyhedron is basically a triangle. Where again, each of these points on the triangle is an experiment you would actually perform. And once you've performed all of these experiments, you get the responses and you rank them in order of best to worst. And you take the worst performing experiment and you reflect it through the midpoint of all your other experiments. And then depending on which version of this algorithm you're using, the magnitude of this reflection can be adjusted to either enable expansion, which allows you to accelerate the movement of this simplex across the design space, or contraction, which allows you to ultimately converge on the optimum once you've found its location. Now, this approach is extremely simple, very computationally inexpensive, but because it relies on the gradient of the response surface, it always suffers from converging on the closest optimum from its starting position. It's also very data inefficient, so it only uses the last few experiments to make a decision on where to sample, rather than using all the data that it's collected throughout. So this is just an example I pulled from a paper in 2011 by a team from Nottingham where they applied this simplex algorithm to a self-optimization. And in this system, we were looking at the esterification of ethanol in supercritical carbon dioxide. So the reaction itself is fairly simple. Diethyl ether was selected as the desired product, and then you have potential byproducts forming from competing dehydration and dehydrogenation pathways. The setup involved two pumps, so one for delivery of the ethanol, one for delivery of the CO2, and then they flowed through a packed bed reactor of alumina. The reaction mixture went through a sample loop, which enabled direct injection for gas liquid chromatography analysis. The pressure of the system was all controlled by a BPR. So 3 variables were selected for this optimization. So the pressure of the system, the flow rate of the CO2 gas, and the temperature of that packed bed reactor. And in this case, the simplex algorithm was able to optimize the reaction from about 2%, where they started it in this bottom corner, up to about 80% in this top corner without any human intervention. I guess the problem that was highlighted here is that the optimization still took a lot of experiments. So I haven't individually counted all of these dots, but it's probably at least over 100 experiments on what is relatively a simple problem. Now, it wasn't an issue in this case because the starting materials are relatively cheap. So ethanol, for example, very easy to get hold of, but this isn't always the case. And if you want these technologies to be applied to something of higher value, such as API syntheses, then reducing the number of experiments by using more efficient algorithms really does become crucial. Now, the last talk just did a fantastic job of introducing Bayesian optimization, so I'm just going to reiterate it a little bit here, but essentially it's well known to be efficient for black box optimizations of expensive to evaluate functions, which chemical reactions really are an example of. You're literally having to use expensive materials, and the experiments take a significant amount of time to carry out. So in contrast to simplex, Bayesian approaches model all of the data and use this in combination with an acquisition function to determine the next sampling point. Most models are based on Gaussian processes. So this is a distribution of all possible functions which fit your current data set. And this has the benefit really of providing a mean function to represent your current predictions, as well as confidence intervals to represent your uncertainty. And then you maximize this acquisition function over the surrogate model, balancing the exploration of regions of high uncertainty with the exploitation of current knowledge. So in this way, Bayesian optimization really is aiming to rapidly converge on the optimum whilst collecting enough information to be sure that it's actually found that global solution. So we've tested Bayesian optimizations on quite a few examples within our lab now. One of the simple ones is shown here. So this is the nucleophilic aromatic substitution reaction of 2,5-difluoronitrobenzene with morpholine, and you can get formation of both the ortho and para regioisomer, as well as this di-substituted product here. And similar to the previous simplex example I showed, we wanted to optimize this reaction just with respect to 3 variables, so keeping it relatively simple. And in this case, this was residence time, the equivalence of that morpholine, and the temperature as well. Now, whenever you were running these Bayesian optimizations, you first have to initialize them by providing them with some initial data to model. And we typically collect this via Latin hypercube sampling. So this aims to give a good distribution of points over that entire design space. In this case, the first 7 experiments, shown by these blue squares here, were all from the Latin hypercube, and then the algorithm takes over to do refinement from that point. And in this case, we can see experiments 8 and 9 actually corresponded to a lower yield than that from a Latin hypercube. And when we looked at the data, found the algorithm was actually exploring regions of the space at this point, but it was still uncertain with, which weren't necessarily captured very well within the Latin hypercube. And as soon as it was happier with the information it had got, it went to converge within the optimum region. And you can see the next 4 experiments after that point were all very similar yields, and were all located up in this top corner here. And so we were satisfied we could terminate the optimization at that point. And really what I wanted this example to highlight is that in contrast to simplex, the Bayesian optimizer on a very similar 3-variable problem was able to optimize it in just 13 experiments compared to more than 100 in that previous example. Okay, so what I want to do now is just give a few case studies of where we've used Bayesian optimization to achieve different types of self-optimizations. So first one of these is multi-objective optimization. So as I mentioned before, it's becoming increasingly important to include environmental considerations within our optimizations while still really achieving a productive process. The problem with this is that a lot of your economic and environmental objectives are often conflicting. So what this means is that the optimum for one usually isn't the optimum for the other. Now, one of your solutions to this is to try and use weighted objective functions. So this is where you basically just combine each of your objectives into a single function and apply different weightings depending on how important you view each of those objectives to be. And if you do this, then you can feed this function directly into just one of your single objective optimizers. The problem is that if you don't have any prior information, these weightings are somewhat arbitrary. They can be very difficult to predefine. As well as that, depending on what you define, you'll only ever achieve a single compromise solution between these two different objectives. Now, in reality, multi-objective problems have a set of solutions called the Pareto front, and each of these solutions represents a compromise, so a particular optimal solution. So in this case, you can see if you were trying to maximize both Y1 and Y2, you would ideally be up in this space. This is infeasible because for conflicting objectives. So instead, one of your best optimal solutions will be one of these red circles here identified on the Pareto front. And these are classified as non-dominated solutions. And that means you can't improve one of the objectives without having a detrimental effect on the other for any of these points. Now, there are algorithms which already existed, which could solve these types of multi-objective problems. The most well-known probably is NSGA2, which is a genetic algorithm. But the problem with these, again, similar to simplex, is they require lots and lots of iterations, which aren't particularly suitable for chemical reaction optimization. And so what we wanted to do is collaborate with the University of Cambridge to develop a multi-objective optimizer more based on these Bayesian optimization principles. And so that's what we did, and we published this work all the way back in 2018 now on this algorithm called TSEMO. So similar to the previous Bayesian optimization I went through, you need some initial space filling data. Again, we did this via Latin hypercube sampling. And then you can build these Gaussian process surrogate models. In this case, you've got two objectives, so you can build a Gaussian process model for both of these objectives separately. You then take a random sample from these Gaussian processes and you use an algorithm in silico, such as NSGA2, to identify what the Pareto front of these models is. Now, this gives you essentially a Pareto front based on your in silico models, and then you evaluate each of these different experiments on the Pareto front for their potential hypervolume improvement. So your hypervolume really in multi-objective optimization is a performance indicator used to measure the volume of space dominated by a solution set. So in this example on the right, if I was trying to minimize both my objectives, my points labeled E here are all my potential next sampling points. And what you do is you have a look at how each of these would improve the hypervolume relative to this reference point in the corner. And the greater the hypervolume improvement, the better your Pareto front will be. And based on this, you can then perform the next experiment, and then this will go around iteratively again, hopefully converging on that trade-off. So we tested this on a couple of chemical examples using these self-optimizing systems. This one's a similar reaction to what I went through previously. So it's another nucleophilic aromatic substitution. In this case, we did the 2,4 difluoronitrobenzene instead, and still targeting the ortho product. And we chose a couple of different conflicting objectives. So here we wanted to maximize the space-time yield, which is a measure of productivity, whilst minimizing the E factor, which is a measure of your environmental impact. And this time we did 4 variables, similar again, residence time, morpholine equivalence, and temperature. This time we included the molarity of the reaction as well. So this is what our Pareto front looked like. You can see the black squares of a Latin hypercube sampling. And as soon as we allowed this TSEMO algorithm to take over, you get a very rapid convergence towards this front. So you can see that all the solutions suggested by the algorithm are all non-dominated with respect to that Latin hypercube. The trade-off itself can then be used by yourself, by the user of the algorithm, to decide what a reasonable point on this is for the process you're trying to design. So in this case, you can see that you can have a very low E factor at about 2,500 on your space-time yield. And what you can get is it's quite a significant increase in the space-time yield without much effect on the E factor. And this corresponds to decreasing your residence time while maintaining a low equivalence of your morpholine. And then you hit this sort of turning point on the front where any further increase in your space-time yield would have to come at a cost at a significant increase in your environmental impact. And indeed, if you look at the data, this was corresponding to a significant increase in the morpholine equivalence of the amount of waste you had from that process. Another advantage of this approach as well is it does allow you to differentiate between points with the same response for one objective. So a single objective optimizer would view all of these as the same, but we can actually see that you can almost double your space-time yield whilst maintaining the same E factor across these data points down here. To show another case study for it, we also did an M-benzylation reaction. So this is just a typical alkylation reaction you might see. And we wanted to just form a secondary amine and try and minimize this amount of tertiary amine that was forming. So again, we were maximizing the productivity of this product and minimizing the percentage impurity. Similar for variable optimization. And again, you see a very similar Pareto front being generated in this case. Similarly, you can sort of try and dissect the Pareto front and understand what each of these points are corresponding to in terms of conditions. So we see we can increase our productivity by increasing concentration at low temperatures. And then you've got to increase the temperature to reach higher levels of productivity, but naturally that starts to increase the amount of impurity you're forming in the reaction. And really from a process design point of view, this information is quite beneficial because really it can be reevaluated at any point during your during your development of the entire manufacturing process. So for example, if you had a reaction you wanted to optimize, and you could only manage 5% impurity in the downstream workup, then you can use this graph to say, okay, the best productivity I can obtain at 5% is roughly 250 space-time yield. But if a workup team later came to you and said, actually, we can now manage 7.5% impurity, you wouldn't have to re-optimize the reaction for those conditions. You can just read off your conditions well and see you can now increase the productivity to 300. Okay, so everything I've talked through so far has been on single-step self-optimization, but as I said at the start, our group's quite motivated in looking at multi-step flow reactions to really get these benefits of developing these uninterrupted reaction networks. The problem with when you start combining reactions directly together is that you start to introduce interdependencies between the steps. And what this means is that you get an exponential increase in complexity. So where if you had one step, you might have 100,000 different possible reaction combinations. Two steps doesn't mean you would have 200,000. It would instead mean you've now got 10 billion different reaction combinations. And so we really wanted to see if some of the benefits we saw for single step optimizations could be translated to that of multi-step. And people had already started to do some work in this area. So for example, you can set up your self-optimizing platforms where you have multiple reactors all put in series and then have a single endpoint analysis. So just HPLC in this case. The problem with this is that you actually miss quite a lot of information throughout the process. By just sampling from the end, you don't see any formation or consumption of key intermediates, which can be quite important. You can also do multi-point analysis. So at the output of each reactor, you can have different analytical instruments. The problem with this is it becomes prohibitively expensive. And indeed, we wanted to try and find a way where we could do these multi-step optimizations in this fashion, but keeping it accessible so that most labs would still be able to take up this technology. So what we developed was a multi-point sampling approach using a single online analytical instrument. So as I said, most cases we do a HPLC because we do a lot of our work within the pharmaceutical industry. So in this case, what we did was daisy chain two sampling valves together and put them in loop with the HPLC. And what this very much allowed us to do was to within the code say exactly when each of these sample valves should fire as each reaction reached steady state. So what we could get was full quantitative HPLC analysis of both steps within a single run. Another thing we wanted to consider moving into multi-step systems is that we don't want to have to run multiple optimization campaigns. So one thing we had noticed when applying these Bayesian optimization approaches is that sometimes the optimization didn't always work very efficiently and didn't always identify the global optimum. So we were often using this acquisition function called expected improvement. And within this, you have to define this value here, epsilon. And this is a measure of the exploration and exploitation trade-off. And if you get this value wrong, it can have quite a significant impact on the efficiency of your optimization. So if you set it, for example, to explore too much, you end up with an algorithm which is very much like random sampling. If you set it to exploit too much, you end up with a very greedy algorithm, which doesn't necessarily find that global optimum. And so instead, we wanted to de-risk that for telescoped optimizations because we really couldn't afford the materials to run these more than once. And so what we looked into doing was integrating this adaptive expected improvement function, which had been developed by one of our collaborators at the time, IBM. And the idea of this is that you allow this parameter to change throughout the optimization. So you allow it to dynamically adjust itself based on this concept of contextual variance. And what they found was that when they ran it on this camelback minimization problem, all of the gray shading beneath this line are examples of what would have happened if you happened to select the best possible expected improvement value. And all of the gray shading above this line is what happens if you don't pick that optimum value. And so you could see in about 95% of cases, applying the adaptive expected improvement actually meant that they were able to find the global optimum without risking a poor optimization performance. So with the analysis and a slightly different algorithm approach in hand, we decided to apply this to a new case study. This was actually in collaboration with UCB at the time. We were interested in forming this aryl ketone from this aryl bromide. So what we were looking at was the first step was a HEC palladium catalyzed cross-coupling of ethylene glycol vinyl ether to give this vinyl ether intermediate. This can then undergo intramolecular cyclization when heated, and then the ketal can be selectively deprotected in the presence of this Bock group to give the desired aryl ketone. The setup looks very similar to how we would for the single step ones, except we now have this integration of two sampling valves directly daisy chained with the HPLC, and we would introduce the acid for the selective deprotection downstream into a second reactor. Similarly, we kept this as a 4-variable optimization, so residence time in the first reactor, equivalence of our ethylene glycol vinyl ether, temperature of the first reactor, and the acid ratio being introduced downstream. And we were targeting the overall yield of our desired compound. Now, overall, we were able to run 32 telescoped reactions over about 45 hours, and we obtained an overall yield of 81%. And this was identified after just 13 experiments. So similar to before, we ran an initialization with a Latin hypercube, and it then only took the algorithm 4 experiments to identify what was ultimately the optimum yield. Now, in this case, we'd already made up the solutions, so we might as well let the optimization play its course. We allowed it to run for 32 experiments, and we saw the algorithm behave as pretty much as expected. So a lot of the time it hung around the optimum value, just checking for any potential secondary optima, and then every now and then it would go and explore a different part of the space, again, just making sure it's found that global optima. Now, in terms of a comparison to previous single-step optimizations, just as an example from one of our previous papers, a single-step one would take 42 reactions conducted over 26 hours, with the optimum identified after 16 experiments. And so we were still on a comparable scale with those single-step optimizers. We can also plot out the data in a similar fashion and try and understand what's going on with respect to each of the reaction conditions, although as you start to add more variables and more steps, this becomes harder and harder to represent on these plots. So I think this is actually a 6-dimensional plot, but quite difficult to understand. Nevertheless, we found that high temperatures and equivalence in the first step works really well. Moderate temperatures seem to be favoured, so around 140 degrees. And then the equivalence of acid, represented by the size of the spot, seem to have very little effect. You can see in this optimal region, the overall yield's very similar regardless of that. And then we also favoured long residence times in that second reactor. And what you can also do is pull out the coefficients from the Gaussian process model after the optimization and use these to determine the relevance of each of these as well. And just as an example, as I said, you can see that the equivalence of acid is having very little effect on the overall yield just based on the color of those spots. Similarly, the higher these values, the less of an impact they have. And you can see this value is much, much larger than any of the other variables in this case. Now, the real benefit in this case of the multi-point sampling was that we could have a look in a much more detail at what was going on at each step of the process, so within each reactor. So what I'm showing here are the plots from just that first sampling point. So here we've got the conversion of 1, the formation of the ketal 4, and the formation of vinyl ether 3, all within that first reactor. And what we saw that conversion at all these different reaction conditions were quite good. And what was differing was the sort of ratio between this intermediate 3 and this ketal product 4. As you can see, at moderate temperatures, we're forming quite a lot of this vinyl ether intermediate, whereas we're only forming very small amounts of this ketal 4. And if you remember from the previous slide, our optimum was actually located within this region. So it suggested that forming more of this vinyl ether intermediate seemed to be having a more positive effect on our overall yield. And again, then by looking at our second sampling point, we could deconvolute what was happening in that case. So here we're showing the 4 reactions where we had the highest vinyl ether yield. So these are shown by different orientations of triangles. And we're showing the 4 points where we had the highest ketal yield. So these are shown by the 4 other shapes. And we translate this into conditions in the second reactor to see what effect those were having. And we can see that in each of the cases with the 4 triangles, so when we've got a lot of vinyl ether, it doesn't really matter what your residence time or equivalence of acid are, you still get a very good yield of the ketone. So that's clearly very readily hydrolyzed, whereas the ketal starts to require much harsher conditions. And so what this means is that in comparison to what was observed in batch by our collaborators, we actually had a much more favorable competing pathway going directly from this vinyl ether into the RL ketone, so bypassing this intramolecular cyclization. And what this meant is that flow chemistry and optimization in this case actually meant that we were able to achieve a process with much lower temperatures and actually just catalytic amounts of the acid. So just conscious of time, I just wanted to cover one other example. So up to this point, we've only looked at continuous variables, but categorical variables are obviously very important in chemistry, especially when we're looking at catalytic systems where you have different catalytic species and ligands which play a crucial role. Now, these are very hard to treat with typical Gaussian processes, and it's much easier if we can convert them in some way to continuous representations. And this has been done by some groups previously, so using quantum mechanical descriptors, for example. But this can be very difficult to do. It's very difficult to know which descriptors you should include in your optimization without any prior information of their effect. And it's also very computationally expensive to determine these. It does involve a significant amount of pre-work. And so what we decided to do instead was integrate this latent variable Gaussian process modeling approach with our algorithm I talked about in the previous slides, where the categorical variables become represented by these low dimensional latent variable spaces. So the approach is very much data driven, which means the representation is based on the response of the experiments. And this means that this mapping, these latent variable representations, can be adjusted as more information is learned throughout the optimization. And then the proximity of each of these categorical variables in the latent variable space can be used as a measure of similarity. In particular, we were drawn to this approach as it's known to predict well on data with nonlinear similarity, and this is often observed in chemical systems. So, for example, if you had two different catalysts, there's no way of knowing in advance if both catalysts are going to work well under the same temperatures. It's very likely that they would have different profiles. So we wanted to benchmark this approach, our new algorithm, against some of the other algorithms which were already available. Now, benchmarking with traditional test set functions often provides results which doesn't necessarily translate very well to real-world applications. So what we decided to do was benchmark the performance of the algorithm on a series of more chemically motivated test problems. So in this case, we used 5 case studies based on simulated kinetics of catalytic reactions. These were proposed by Klaus Jensen over in MIT in this paper shown here. And each problem was designed to have different characteristics, which was achieved then by varying the catalyst-specific activation energies of the bimolecular reaction. And what you can do is, for example, in case 3, start to include potential side reactions, in case 4, potential decompositions, and in case 5, we actually had a temperature-dependent catalyst deactivation as well. So our algorithm, which we've termed AlaBO, is represented on these convergence plots as the red line. We were comparing this to Dragonfly and Process Optimizer, which we'd selected because both of these had been used a lot in self-optimization platforms, and both were open access and available through Python to use. And what we found across the 5 different case studies, but overall, AlaBO was able to converge at a faster rate in comparison to these algorithms, and was able to obtain within 1% of the optimum value, about 1.4 times faster on average. The important one, I guess, where we had the most discrepancy between the approaches was case 5. So this is where we had that temperature-dependent catalyst deactivation. We ran each of these 10 times to get these plots. And in all 10 cases, our algorithm was able to find the optimum catalyst despite this deactivation, whereas the second best, so the Dragonfly approach, was only able to do this in 70% of cases, which we think lends itself well to that LVGB approach that we incorporated. Once we'd set this up, you can also have a look at some other sort of factors which affect the optimization. So this was just another example of something we looked at, which was the initialization strategy. I guess one of the problems when you've got a lot of categorical variables is you need to collect quite a lot of data about each of them in your initialization. So we were looking at 8 different catalysts in these simulations, and if we were collecting 5 line hypercube points per catalyst, this means you've got 40 experiments before you even start the optimization. So we had a look at what would also happen if we reduce that value to 3 per catalyst, or if we just use a center point for each catalyst. So that's a center point with respect to the continuous variables. So you just have 8 starting points. And what we saw actually across the 5 different case studies is that it was actually more efficient to give the algorithm less data and allow it to take over sooner than it was to give it extensive amounts of initialization data. And so using this, one of my master's students quickly did an experimental demonstration, just looking at this simple Suzuki reaction. And I guess the main point here is that we looked at 6 different ligands. So this is the discrete variable we included. And the way we modified the equipment to do this was basically just place a multi-position selector valve at the inlet of one of the pumps. And this allowed us to draw from 6 different catalytic reservoirs for the optimization. Now, using the center point initialization strategy, we just did 1 experiment per iteration for a total of 25 experiments. So we gave ourselves a very strict experimental budget here, mostly based on time constraints. But nevertheless, even just after 10 experiments, we were already able to identify a very positive solution, getting 93% yield with a turnover number of 95. And this corresponded to the use of Cy-John Foss with high temperature, enabling a high yield to be obtained whilst not using an overly large catalyst loading. In the interest of time, I'll just skip those last couple of slides. And I guess moving on to a conclusion and outlook, hopefully what I've shown is that multi-objective optimization really is a powerful tool for simultaneously addressing environmental and economic issues. We very rarely now just optimize our reactions for just yield, especially as these multi-objective optimizers become more and more efficient. I've also shown some of our initial work towards multi-step and mixed variable optimizations, but I point out here these still have a lot of limitations, which the group are actively working towards improving and solving. One of the main limitations I see with these systems still is that there's a limit on the number of experiments we can carry out because of the amount of material you still have to use. And these have been improved quite a lot recently by people developing droplet flow systems, but still the optimizations we've looked at are usually on a very low dimensional space with respect to those categorical variables. So only looking at 6 ligands, for example, is still quite restrictive. This is sort of further emphasized by the fact that every time we run a new optimization on a new reaction, we need a new set of initialization experiments. And this really does account for most of the experimental time. And so if we can find ways to transfer learning between different types of reactions, there's really a potential to accelerate some of these optimizations. So with that, I'd just like to thank you all for listening. I acknowledge everyone in my group again, as well as all the funders of the research.